Dr. Deng, are you ready?
Yeah.
Yeah, can you turn your camera on?
Yeah, sorry.
Yeah. Okay, good morning, good afternoon, and good evening. Welcome you again to the World River and Delta System Source to Sink webinar series. So this is Paul Liu from NC State University. This talk series is co-sponsored by National Science Foundation, North Carolina State University, Louisiana State University, State Key Lab of Estuarine and Coastal Research, Utrecht University, and the CSDMS. And today is a very delight to invite Dr. Deng Kai Deng from ETH, Zurich, and Tongji University come here talk about meteoric beryllium 10-9 as a denudation proxy in the fast-eroding Taiwan mountainous rivers. So today, this talk marks a little bit a milestone. This is number 100 talks. So hallelujah! This I think we need deserve a celebration. Since during the pandemic, I think we can as the English way to say, to eliminate. So bad to good, So we take advantage of this opportunity and the technology. We are able to gather online in the Source to Sink community, talk about so many interesting river, delta, and depositional system. So you can reach all previous archived recorded talk on the YouTube channel or on the B station. And at the same time, we also maintain a Source to Sink Twitter account. So every week, we will send out the note announcement about the coming talks. So you're welcome to follow us. So Source to Sink on Twitter. And next week, next Wednesday, I know next week will be the Chinese or Asia Lunar New Year. Many colleagues in mainland China, Taiwan, Korea, Japan, Vietnam, including Indonesia, they will celebrate the Lunar New Year. But during this pandemic, the best thing to do to celebrate the New Year is just to come online to attend that kind of academic feast. So next week, Professor Rivita Bookman from Haifa University, Israel, will come here talk about the development of the Nile littoral sail, the longshore transport in the Holocene. So please mark your calendar at the same time next week. So Dr. Deng Kai is now a postdoc fellow at ETH Zurich. And as you can see here, originally he graduated from Tongji University with a bachelor and a PhD degree. And also he went to Germany for a visiting student, a joint PhD student with the Freely University, Berlin. And after that, a short-term postdoc and also a postdoc fellow at ETH. His research, mainly the development and application of geochemical proxies, particularly the beryllium 10 and 9 ratio, and in the Earth surface processes. His previous work focused on denudation process and sediment source to sink process in the small mountainous rivers of Taiwan Island. And now is switch to a boundary exchange process, land-sea interface, and impact oceanic element cycling, use the tracer, geochemical tracer, beryllium 10, REE. So Dr. Deng, now you can share your screen and put a presentation mode.
Yeah, I will show my screen now. Yes, hi everyone. It's indeed a very great honor to present in this famous Source to Sink webinar. And really many thanks to Paul Liu, as Professor Liu mentioned that this is the 100th talk of this series, and it's a big honor to me. And yeah, so I will start now. Hi everyone, I'm Kai, a postdoc from ETH Zurich and Tongji University. Today, my major topic is about my PhD work at GFZ Potsdam and also Tongji University, which is related to the novel denudation proxy Meteoric brain time to stable brain line ratio. Today, I will introduce a little bit about method development of this proxy and also its application in the fast-eroding Taiwan mountainous river basins to quantify the millennial scale denudation rates and also its controlling factors. So it's worth mentioning that this work cannot be done without the support of my previous supervisors, including Professor Yang, who is also here, and also Dr. Whitman, and also Professor Van Brandenburg. And also many thanks to other collaborators, including Professor Menglong Xie, Professor Yuanping Zhang, and Professor James Liu. So let's start with the background. So I guess many people are very familiar with this figure. To understand the Earth surface material cycling, the source-to-sink transport of sediments from rivers to the oceans is a key process. And it is well known that the East Asian rivers, including many large river basins like the Changjiang River and also the Yellow River, and also many other small mountainous rivers, play a significant role in the global sediment budget. In particular, when we zoom in this region, the small mountainous rivers contribute a disproportionately high sediment yield, a sediment flux, because it's high sediment yield as shown by this red color. And as an active mountain belt, the Taiwan origin bears a lot of small mountainous rivers with very high sediment yield. You can see a plot here with sediment yield versus the drainage area. So these red dots are from Taiwan rivers. You can see that like such a small river can contribute a sediment budget similar to many of these large river basins. So you can consider this as a hotspot of sediment yield in this Taiwan island. And what is the reason that makes the Taiwan mountainous rivers erode so fast? We think that the first reason we need to mention is about the tectonic background. So let's move back like a little bit time backwards to the 6 million years ago. It's as shown here. So around 6 to 7 million years ago, Taiwan Island was not an island. It was just marine sedimentary sequences deposited in the East Asian passive continental margins. However, since such time, the collision between Luzon Arc and also Asian continent squeezes all these sedimentary sequences together and finally lead to the uplift of the Taiwan origin that we can observe now. So such active tectonics can lead to many earthquakes in this region that can provide enough energy to break down rocks into loose sediment materials. So that's the first reason that may cause such high sediment yield. In addition, the Taiwan island is attacked by frequent typhoon events, such as 3 to 4 events per year. And such typhoon events can not only provide energy to break down rocks into loose materials, but also transport these materials from hill slopes to the river channels and then later to the oceans. So the combination of both factors can lead to the extremely high sediment yield in the Taiwan origin. And so what is the significance of the erosion process in the Taiwan mountainous rivers? We can think about two perspectives regarding sediment cycle and also carbon cycle. So here is a figure showing the sediment discharge from all the rivers in the Taiwan island. You can see that the river sediment from Taiwan island can be delivered to the surrounding seas, including the Taiwan Strait, South China Sea, and also Pacific Ocean. Such delivery does not only include the sediment, but also particulate organic matter. And in total, such a sediment amount can be comparable with the large river basin as the Yangtze River in China. And such sediment and organic material delivery can affect the biogeochemical cycling process in the surrounding seas. That's the first part of the significance. And the second part is related to carbon cycle. So erosion process, it can control multiple mineralogical and organic matter transfer pathways at Earth's surface. For example, the silicate weathering, sulfuric-driven carbonate weathering, organic carbon burial, and also organic carbon oxidation. All these processes can lead to a carbon dioxide consumption or carbon dioxide release. And these processes are all controlled by erosion process to some extent. Hence, we can also consider the Taiwan Island as a hotspot regarding the global carbon cycle. So it is essential to quantify the denudation process in these Taiwan mountainous rivers in order to understand the marginal sea sediment budget and also the global carbon cycle. So to quantify erosion rates or denudation rates, there are multiple methods across timescales. It is also worth mentioning that the denudation rate here means the sum of erosion rate and weathering rate. Sometimes people mix both concepts together, but I want to clarify it here, as we may mention this concept many times in the later slides. So the integrated timescale of denudation rate is dependent on the chosen method. For example, we can use sediment gauging to quantify the denudation rate over a decadal scale and annual scale. And then we can use cosmogenic nuclide to quantify the denudation rate over a millennial scale and semochronology over a million-year scale. When applying these methods in Taiwan Island, there may be some limitations for each of them. I won't go into details here, as our focus is only in the second part, which is about the millennial scale denudation process. We consider this process is important because such time scale is less sensitive to short-term events, and also it is related to modern topographic build-up. So to quantify the millennial scale denudation rates, commonly the cosmogenic in situ barren time measured in course is the first choice. However, when applying this method in Taiwan Island, there are two major limitations. The first one is that the Taiwan origin has a lot of outcrops of coarse-pore lithologies, including marble and slate. Such lithology make the coarse burning in situ barren time not so applicable. And the second limitation is that the in situ barren time requires a large sample amount for measurement, such as several kilograms, and it makes it difficult to be applied in the precious sediment core samples. So here, our focus is on an alternative approach, which is meteoric barren time, the in situ barren time sister nuclide. So here is some principles about the meteoric barren time proxy. So different from the in situ barren time that is produced in rock-forming minerals at Earth's surface, meteoric barren time is produced in the atmosphere and later scavenged by rainfall to the Earth's surface. It then binds tightly to the soil particles and later eroded to the river channels and transported to the sampling location or to the oceans. So the meteoric barren time proxy has been widely applied to determine Earth's surface dates and rates, including depositional age, soil residence time, and also erosion rate. But in our approach, because meteoric barren time is mainly measured in sediment coatings by chemical lynching, and it is enriched in fine-grained particles, so we use meteoric barren time normalized to stable barren line to reduce such grain size effect. And in principle, how can we link the barren time ratio with the denudation rate? A simple example is that at a stable Earth surface with slow erosion, the soil particles has a longer residence time at Earth surface and thus can accumulate more meteoric barren time from atmosphere. So when it is eroded to the river channel and to the sediment, we can measure a higher meteoric barren time concentration and thus a higher barren time ratio. So in short, it means that the meteoric barren time ratio and erosion rate are anti-correlated. So till now, meteoric barren time proxy has been applied in many river basins, but mainly in large river basins such as Amazon Basin, Potomac Basin, and also Ganga Basin. So in these studies, meteoric Brent-10 derived denudation rate and in situ Brent-10 derived denudation rate mostly agree within a factor of 2, but sometimes there may be larger differences and can reflect true geological variability to which both methods respond differently. So there are several advantages about this Meteoric Brent-10 proxy. The first is that it is measured in sediment coating and only requires a small sample amount for analysis, like 1 gram, and thus it is quite suitable to be applied in precious sediment core samples in which we don't have so many samples lying around. And the second advantage is that it does not require the presence of pores because it is extracted from sediment coating and can be applicable in marble-based basalt and also shale, which is not readily applicable for in situ Brent-10. And we consider that this proxy can be applied in the Taiwan rivers as many of the prerequisites are largely met in Taiwan mountainous rivers, and some of them can be independently constrained. So here I will give you some more details about how can we use this proxy to quantify the denudation rate. So here is a calculation framework of this proxy. And here, this is a simplified version to establish a link between denudation rate and Brent-10 ratio. All these parameters shown here can be quantified using multiple approaches. Here is a selection of methods. So for the baryon isotopic composition in reactive and mineral fractions, so these 3 parameters, they can be extracted from different sediment types using different chemical lynching methods. And also for baryon concentration in the source rock and baryon-10 depositional flux to the study catchment, they can be constrained independently using other approaches. So the underlying approaches shown here are those used in our study. And in the few slides later, I will mainly explain how can we constrain the 2 parameters. One is baryon concentration in source rock, and another is the baryon-10 depositional flux. About baryon concentration in source rock, if we apply this proxy in a large catchment, we can simply assume a constant like 2.5 ppm, which is the same as the upper continental crust. But when applying this proxy in small catchments, we can adopt 2 approaches. The first is that we can measure all the baryon concentration from different rock types in the catchment and using the area-weighted baryon concentration based on the areal percentage of each source rock. And the second approach is to establish a linear regression equation between an immobile element, such as aluminum, and baryon concentration in all source rock types. And then we can substitute our measured sediment aluminum concentration into this equation. Then we can get a representative baryon concentration for the specific sample. And the second parameter is the baryon-10 depositional flux, which is the key for the accuracy of this denudation rate proxy. So to constrain this parameter, there are 3 methods available, including the general circulation model, precipitation-based fitting equation, and also soil baryon-10 inventory. So the first 2 approaches are commonly applied over large spatial scale with coarse resolution. And the third approach can derive the site-specific baryon-10 depositional flux and can be more accurate if baryon-10 is fully retained in the soil column. So here we will compare, to evaluate the reliability of each approach. We will compile literature flux data from all the 3 approaches and compare between each method to see the bias and reliability of each method. So here is the data set we compiled. So we compared measured baryon-10 depositional flux, including precipitation-derived baryon-10 depositional flux and soil baryon-10 depositional flux, and compare this measured flux with the model-derived flux. We find that the precipitation-derived flux are generally higher than the GCM-derived flux and can be even 2-fold higher for half of the data set. However, the soil-derived Brenten flux generally agree with GCM-derived flux within a factor of 2 for more than half of the data set, but the rest are even lower. So by careful evaluation of the uncertainty in each method, we propose that the short-term rainfall-derived flux may be subjective to a time interval bias and thus lead to an overestimate. However, in the soil-derived Brenten depositional flux, if the Brenten is not fully retained in the measured soil column, there may be some Brenten loss and thus lead to underestimate of the depositional flux. So that's the reason for such pattern. And we propose that the realistic Brenten depositional flux over long term should stay between soil-derived and GCM-derived flux. So this is a global scale pattern, but as we want to focus on this specific region, the Taiwan island, we want to constrain a site-specific Brenten depositional flux. To do that, we went to the Taiwan island and collect some river terrace profiles. So all these terrace profiles were determined by carbon 14 in order to get the age. All the depositional ages for these terrace profiles are in the Holocene. And we collect all these terrace profiles and measure Brenten concentration in these samples so that we can calculate Brenten depositional flux using this equation. So this parameter is a Brenten inventory in terrace profile, and this is a depositional age. This ratio drives the long-term site-specific Brenten depositional flux. Here are the results and comparison with some other method. So this short line means the measured Brenten depositional flux from terrace profiles. As mentioned earlier, the Brenten may not be fully retained in the soil profile. As such, it may only represent an lower limit estimate. So we evaluate all the sources of uncertainties in each terrace and modeled the plausible range of Brenten depositional flux as shown here for each terrace. So we find that there is an overlapping range in the Brenten depositional flux, which is shown by this red bar, around 0.8 million atoms per square centimeters per year. And we found that this range is indeed higher than the measured terrace-derived flux, but slightly lower than the GCM-derived flux. So this is consistent with the global observations. And thus, we recommend to use such flux range for future applications of meteoric Brenten proxy in the fast-eroding Taiwan origin. So as mentioned in the previous slides, we already got good constraints on some of the parameters in the meteoric Brenten framework. Now we can apply this proxy in the Taiwan mountainous rivers. So we focus on rivers draining westward and also eastward. In fact, in the Taiwan origin, there is a clear east-west pattern in lithology, topography, and also climate. So regarding lithology, the central part of Taiwan island is dominated by claystone like slate. But in the west and east part of the Taiwan origin, it is dominated by sandstone and schist marble, respectively. But regarding the topography, the central part and east part of Taiwan island is dominated by steep topography, like higher than 20 degrees in slope. But the western Taiwan is featured by the foothills and thus with gentle slope. So about the precipitation rate, in general, the Taiwan island is characterized by high precipitation rate with an average annual rainfall of 2.5 meters per year. And it also generally increases with elevation. So this east-west pattern in all these parameters will also be discussed later in our Brenten applications. So here I show some field photos of our studied catchment, including the Choshui River in the west and also Liwu River in the east. You can clearly see from these photos that the sediments in the Taiwan rivers are really poorly sorted. So in this case, we collect these sediment samples and then we sieve them to a narrow grain size fraction to reduce the potential sampling bias. So here is an outline of our meteoric Brenten application in small Taiwan mountainous rivers. They can be divided into 3 parts. So the first part, we applied this proxy in the Choshui River. which is the longest river in Taiwan and drains a wide range of research units. So here we found a clear research control on the denudation process. And in the Liwu River in the east, with a smaller drainage area and polar sediment mixing, we found that the effect of stochastic landsliding cannot be properly averaged out and can affect the denudation rate measurement. And for the third part, we apply this proxy in a sediment core drilled in the Choshui River mouth so that we can reconstruct the paleo denudation rate since the last glacial period. I will explain these studies one by one. So let's focus on the Choshui River at first. Here, the red dots means the Meteoric Brand 10-9 derived denudation rate, and we show the denudation rate versus the distance upstream from the river mouth. You can see that in the headwaters with slate dominance, the denudation rate is highest with 4 to 8 millimeter per year, which is similar to the range from the thermochronology derived exclamation rate in the mountain core. And when it moves to mid-lower stream, we can find that the in situ Brand 10 derived denudation rate, this gray squares, and Meteoric derived denudation rate generally fall within a narrow range of 1 to 2 millimeter per year and much lower than the headwater values. So what causes this special pattern of denudation rate variation? To explain this pattern, we invoke the stream pole incision model as shown here as a simplified version. So the denudation is commonly considered as controlled by three processes like topography, climate, and lithology. Here, this simplified equation shows the link between denudation rate and these parameters, including channel steepness, precipitation, and rock erodibility. So in general, in previous studies, people found that in the origins, there may be a clear relationship between the erosion rate and channel steepness, which can be considered as area normalized local slope. So such correlation suggests the topographic control of denudation process in some mountain belts. However, this conclusion is inconsistent with our observations. We found that in the Choshui River, our denudation rate is only poorly correlated with the basin average channel steepness. You can see from these low R-square values. And also for the climatic metrics, the basin average precipitation rate only varies within like 15% for the mainstream basins, and such a small variability cannot explain the 8-fold change in denudation rate. So it means that the topographic and climatic metrics cannot explain the spatial pattern of Meteoric Brand 10-9 derived denudation rates. As such, does lithology play a role here? So in the Choshui River, it drains a wide range of lithological units, including the western foothills, Sichuan sandstone, and slate, backbone range slate of Eocene and Miocene age. And all these lithological units shows a spatial variability from upstream to downstream. And it is also clear that there is a clear decreasing trend for the Miocene slate from upstream to downstream. Such variability thus hint at a non-uniform rock erodibility. So to take this factor into account, we slightly modified the stream pole incision model by including the lithological variability. In principle, we allow the rock erodibility to vary based on the area percentage of each lithological unit. As such, we can derive a parameter called lithology adjusted channel steepness. And we found that this parameter can indeed well explain the denudation rate variability based on the high R-square values. And such plot is only based on our Meteoric Brand 10-9 derived denudation rates. When we incorporate the in situ Brand 10 data from West Taiwan, we found that such arguments still stand, which shows a good correlation between denudation rate and lithology adjusted channel steepness. So to conclude for this part, we propose that the lithological heterogeneity can alter the coupling between surface denudation and channel morphology. Then let's switch our focus from the western Choshui River to the eastern part, the Liwu River basin. So we collected mainstream sediment samples at 3 locations and 3 major tributaries for beryllium isotopic analysis. So here is the mainstream profile for the meteorological metrics and also topographic metrics. We found that in our sampled mainstream basins, the meteorological metrics and topographic metrics show a relatively stable value, and thus it hints at a potentially consistent denudation process in our studied segment. However, our measured data shows that it is clearly not the case. So this plot compares denudation rate from different methods. These blue symbols are the Meteoric Brent 10-9 derived denudation rate. It shows not so clear downstream pattern and a very high denudation rate from 10 to 30 millimeter per year. And such variability is not only seen in our method, but also from multiple methods, including thermochronology, in situ Brent 10, channel incision, and sediment gauging. We also found that in the mainstream, our measured rates and also rates from the sediment gauging and also channel incision can all exceed 10 millimeter per year, which is extremely high, even for over global scale in other active mountain belts. So what is the mechanism to cause such a large variability, like 1 order of magnitude in the denudation rate in such a small basin? So in the Liwu River, the sediment transport is dominated by rainfall-triggered stochastic landsliding, and we consider that as the beryllium concentration in soil is relatively high, and beryllium concentration in bedrock is relatively low. So we invoke the dynamic soil bedrock mixing to explain the variability in the denudation rates, which is caused by the stochastic bedrock landsliding. And such argument is also evidenced by some previous studies on organic carbon-14 data measured in Liwu River suspended load. So this figure shows that this figure shows organic carbon-14 data measured here, and it can be used to indicate the soil bedrock mixing based on the fraction of modern carbon. Here, this fraction varies within an order of magnitude, and it suggests the mixing between the biospheric modern carbon in soil and also old petrogenic carbon in bedrock. So we can use this organic carbon-14 dataset and combine this dataset with a soil bedrock carbon-14 mixing model to calculate the carbon-14 derived contribution of bedrock to the sediments in a general way. And then we can convert such bedrock contribution to the model denudation rate based on end member erosion rate from soil and bedrock. So this blue shade is the model range of denudation rates. And we found that our measured estimates are indeed falling within this range. So it thus shows that the stochastic bedrock landslides in the Liwu River can indeed explain this extremely high denudation rate and also the large variability. So here we propose a schematic plot to show this pattern. So as the Liwu River is characterized by fast sediment transfer, polar sediment mixing, so sediment at different locations can be transported during different, for example, typhoon event or storm event, and can have different mixing ratio of landslide and soil, and thus potentially different denudation rate measurements. So the previous studies we just introduced is only about the modern process. However, in the geological timescales, such as the last glacial period, there may be a large variability in environmental conditions, for example, the climate conditions, and such variability may also affect the denudation process. So for this purpose, we move our focus to the Choshui River mouth, where we collected, our collaborators collected a sediment core named JRDS, and this core has a length of close to like 100 meters and with an age as old as 80 Ka. So we collected 15 core samples from this core and used them to measure baryon isotopic composition and thus convert such composition to the parallel denudation rates. So the first figure is our parallel denudation rate results. So you can see that our parallel denudation rate in the Choshui River shows a very complicated pattern. It decreases at first and then decrease, and increase again. So such pattern is very complicated, but it's also confirmed by some tributary data in the Chen-Yulan River as these open symbols. It also shows an increased trend in the Holocene. So we compared our denudation data with some global scale climatic metrics, such as deep sea delta O18 and also atmospheric PCO2. However, we found that there is no clear consistency between these metrics from the perspective of trend and also from the values relative to the modern data. So we can find that in the modern times, the benthic O18 is the lowest value over the last glacial period, and the PCO2 is the highest over the glacial period. However, our denudation rate fluctuates from the modern data, which is shown by this dashed line. So since we consider that the global scale climatic metrics may not play the role, then what about regional scale climatic metrics? So we compare our denudation data shown here with the monsoon intensity proxy. For example, the speleosome delta O18 measured in Asia caves. So you can find that before the deglacial period, so from from MIS5 to MIS2, this trend is consistent with the speleosome delta O18 data. It thus hints at the potential control of monsoon precipitation on the denudation process in the Choshui River. However, since the last deglacial period, our denudation rate decreases at first and then increase again. Such pattern is inconsistent with the monsoon precipitation, which stays at a relatively high level during the whole Holocene. So what causes this increased trend? This inconsistency is very interesting. And for now, one of our hypotheses is that this is when the change of sea level kicks in. So in this part, since the last deglacial period, the sea level increases rapidly. And as such, the base level of the river channel will also move upward. So in response, the river channel will adjust to a new state with gentle slope. As such, the denudation rate will decrease during this rapid sea level rise interval. However, since the early mid-Holocene, the sea level stays at a relatively stable level, and then the river channel will continue to incise in response to the high precipitation rate shown here, and thus the denudation rate will increase gradually again. So this complicated denudation rate pattern and comparison with regional scale climatic metrics shows a two-stage control of denudation process in the Choshui River since the last glacial period. So here is a conclusion. So in the West Taiwan, we found that the lithological heterogeneity can alter the coupling between denudation and channel morphology. And in the Liwu River, the stochastic bedrock landslides can cause the high values and also large variability in the denudation rate measurements. And when we look back into the time, we find that since the last glacial period, monsoon intensity and sea level change can control the basin-wide denudation process in the Choshui River. And our applications of meteoric baryon proxy in the Taiwan mountainous rivers show that the baryon ratio can indeed be a promising denudation proxy in fast-eroding catchments with cross-pore lithologies. So this is the content of the presentation. And if you want to know some details of this topic, you can check our recent publications listed here. So that's all. But before it ends, I want to advertise for our session in Goldschmidt this year. which is related to the element source-to-sink process. So the title of this session is about transport of particle reactive elements from estuaries to open ocean. If you have any recent work related to this topic, please consider submit to our session. Yeah, that's all. And I'm ready and happy to take any questions. Thanks for your attention.
Oh, thank you, KF, very much for this very interesting, very informative talk about the application, that meteoric beryllium 10 and 9 ratio in the Taiwan. So let's say now, if anybody, if you have any question, please go ahead, unmute yourself. You can unmute yourself and go ahead directly ask Dr. Deng. Joseph, I see you.
Hi. Thank you so much, Deng. I've been following your spree of papers. I don't know if that's the right term for it, but you've been publishing quite prolifically on the subject recently and very interesting work. I have just, if you might be able to go back to the slide where you talked about deposition rate. I had a couple of questions about that, if you don't mind.
Yeah, sure. I think it's somewhere
here. Yeah, that there. So well, I guess I have two questions. So first, with this precipitation, so why do you think it is that the precipitation derived flux is so much higher? Because it would seem to me if it were just interval length, you'd expect it to be stochastic, that you'd expect to have some samples get too much and too little because it's not integrated over long enough. So why would interval length cause it to be uniformly higher?
Yeah, right. Actually, I think perhaps we also discussed this before, right?
Yeah, well, I think I had that question. I had a question when I reviewed your paper.
Right.
So
yes, thanks. Indeed, yeah, we agree that it's a very complicated question for this. I mean, this difference between different methods. So in the paper, we argued that as you mentioned, perhaps people may consider that precipitation can be either higher or lower in the depositional flux. But yeah, our argument is that it may likely be higher because in a paper that only focuses on precipitation rate measurement, they argued that the long-term precipitation rate, so when we mention long-term, short-term here, we mean that short-term is like year scale or seasonal scale, and long-term like decadal scale. And when we compare this short-term, long-term precipitation rate, that paper suggests that precipitation rate over long term can generally be lower compared to the short term observation. And they attribute this to a time interval bias that is similar to the Sadler effect. That's what they mentioned in the paper. And we thought that if there is an overestimation on the precipitation rate, I mean,
so you think it's actually not an overmeasurement of 10 beryllium in precipitation, it's that the precipitation rate itself is biased by short records.
Right.
Okay. That's yeah. I hadn't fully understood that. Okay.
Then we thought it may be related to the overestimate of Brent-10 depositional flux.
Okay. One more question. Maybe it's slide 2 or 2 later, where you have your records from Taiwan.
Yeah.
The next one. This one. Yeah. So so one of those, the 9.05 has a very large range, and the other ones are much smaller. So I was wondering what was the cause of that.
Yeah. So
with the red bars, or maybe I'm misinterpreting what the red bars represent, but.
No, it's also a kind of uncertainty, and yeah, indeed, for this terrace, uncertainty is larger because so this red bar is from the modeling, and because there is uncertainty in each parameter, and then we have a large uncertainty in this. But I think I have a figure that may explain your question. So, so for each terrace, there may be a different source of uncertainty in estimating the Brent denudation flux. And for the 9.03 Ka terrace, as you mentioned, there are two sources of uncertainties. One is about the Brent retention, so it's related to soil pH. And another is about the depositional age in this specific terrace, because the depositional age in this terrace is determined at the lower part of the terrace, but our sampled segment is only at the upper part. And this is a like 100-meter terrace. So it's a huge terrace. So we thought there are two sources of uncertainty. And when taken them into account, we get a large.
You did try to correct for loss of the isotope to in low pH parts of the soil in this calculation.
Correct. Yeah.
Okay. So it's the terrace is large and the effects of leaching uncertain that led to such the large bar for that.
And also the age. Yeah. Right.
Yeah. Okay. Oh yeah, and in the controlling age measurement being inserted. Okay. So thank you. Those are both. Yeah, and I really think this is very interesting work you're doing, particularly with the one I hadn't seen yet. Maybe it's still in a publication process. I hadn't seen yet your profile where you looked throughout the place to see, and that was very, very interesting work. So thank you. This was a very interesting talk.
Thanks a lot for the questions.
Hey, Joseph, where are you from, Joseph?
Oh, I'm at Northumbria University. Although I'm American, and I worked with Paul Bierman on Meteoric 10 beryllium about a decade ago now at University of Vermont, but currently I'm at University of at Northumbria University in Newcastle in the United Kingdom. So that's, but this is, I study glacial processes and geochemistry, but I've continued to use the Meteoric 10 beryllium method in a variety of ways.
That's cool. Okay, anybody else? Any question? Go ahead to ask Kai. Anyway, so Kai, can you explain to me a little bit more the difference, why the denudation rate of the Liwu is much higher than Choshui, the east side of the ridge compared to the western side. So I mean, the tectonic uplifting rate should be very same, the headwater, right? Yeah, and the rainfall, the weather, temperature, everything, the geology, so what's the reason for this almost, as you mentioned, order at least?
So indeed, about the long-term uplift rate, as you mentioned, is likely on the order of 1 to 10 millimeter per year. But if you mean GPS data, then that can be like dozens of millimeter per year. So yeah, but all long-term is in that range, 1 to 10 millimeter per year. And for the Liwu River, it's indeed much higher than the Choshui River. So Choshui River is from 1 to 8 millimeter per year. But Liwu River in the mainstream, as we measured here, is like 10 to 30 millimeter per year. So the difference so the reason for such a large difference between both rivers, we consider is related to the researchable topographic background of both river basins, not really on the long-term uplift rate. So in the Liwu River, it's a small river basin, and also it has a much faster sediment transfer, and also it has a very polar sediment mixing based on our previous studies on strontium neodymium isotopes, which I didn't explain here. But so in a poor sediment mixing regime, the effect of landslides may not be properly averaged out. So it means that you may have a very large variability in the mixing between slowly eroding soil and faster eroding bedrock. And in this kind of setting, you can get a very large range of denudation rate as we modeled here. But in comparison, in the Choshui River, it is a much larger river basin. So I think it's the second largest, so it's the longest river in Taiwan. So it's a large river basin, and there is also landslide there. But that effect of stochastic landslide can be averaged out if the basin size is large enough. That's proposed in previous studies too. So we think it's kind of related, controlled by basin size and also controlled by the mixing efficiency, the sediment mixing efficiency.
Okay, there's a couple things maybe you can consider. One, the slope, and the Liwu, I believe, is much steeper than the Choshui. You know, Liwu may be like this, Choshui may be like this, and so the east side of the central mountain range, you know, in Taiwan, eastern side much steeper, and of course there's more landslide. Second, you can compare other eastern side river like Hualiang River and even the Nanyang River, and then with some western side like Choshui River, Bajang, Wu River, you know, or even Goping, to see this pattern or not. This is a future work. It's what's more work to do. And the last thing to consider is eastern side of Taiwan is facing the storm, facing to the ocean, moisture, the wind, and I believe also play a role to increase the erosion or denudation.
Yeah, that's true. Right.
Yeah. I mean, you can think about in some other situation, like in South America. South America, you know, the Andes Mountain. So if you look at the river flow to the west, I mean Pacific Ocean, the denudation rate, the headwater should be very different compared to those flow to the east, like Amazon, like other river system. I mean, you need some literature comparison or some future work. That will be very interesting.
Yeah, so actually we extract all these metrics as you mentioned about the precipitation rate or channel stability or even local slope or local relief, some metrics like that. But we found that even by taking these parameters into account, it's indeed still hard to explain this extremely high denudation rate. So Liwu River indeed has a higher precipitation rate and also a steeper slope, but it cannot explain like the several-fold increase in denudation rate. And that's why we thought it may be related to some specific stochastic process that can cause such extremely high denudation rate, which we attribute it to the stochastic rainfall triggered landslides.
Yeah, indeed. Okay, so anybody else, any other colleague, student, any question you want to? Okay, go ahead, Lian Qing, Wang, Zheng. Yeah, go ahead.
Yes, can you hear me?
Yes.
Yeah.
Okay, thank you very much for your wonderful presentation. And I am a PhD student. Now I am on my first year, and from the University of Jena, Germany. And so based on your presentation, I have two questions, two basic questions. The first question is about the sample preparation. I want to ask you, is there a large difference between if you prepare in situ temperalium or perihelium 10, and if you prepare sample for meteoric temperalium, is there a big difference between them?
Indeed. So for in situ perihelium 10, they only measure that in course. So they will collect, for example, for like let's take a simple example. We will go to the field and collect several kilos of sediment, and we will sieve them to a cost fraction like 200 to 1,000 micrometers, and then we use this fraction and we process them using chemical lynching and also magnetic separation to get the pure quartz and digest this quartz and measure for in situ perihelium 10. But for meteoric perihelium 10 is different. we only go to the field, collect several grams of sediment, and sieve them to a narrow grain size fraction, in my case, so like 30 to 6 micrometer, and we use sequential chemical lynching method to get the sediment coating and measure that coating for Barium 10 concentration. So the preparation is indeed different.
Okay, so is there, how do you separate in situ beryllium from a meteoric beryllium?
So normally that's not a question for meteoric Barium 10 side, because meteoric Barium 10 has a much higher concentration compared to in situ Barium 10. Don't care about contamination from in situ Barium 10. But from in situ Barium 10, for in situ Barium 10 scientists, they need to remove meteoric Barium 10. And in that case, they use strong acid to remove all those sediment coatings. That's how they remove the meteoric Barium 10. Yeah.
Okay. Thanks. And
but I'm not an expert in situ Barium 10, so I'm not sure if my answers are all correct.
Yes, actually, I'm not quite familiar with the meteoric beryllium 10, so I'm just a beginner. So do you think the major advantage of meteoric beryllium 10 if it applied on denudation rate studies compared with in situ beryllium 10?
So as we mentioned earlier, there are several advantages, and also you can check this paper for some details. So it requires a small sample amount and it doesn't require a course. So I guess that's a major advantage. And if you want to know some details, you can also check this paper.
Okay, thanks. So what do you think is the major uncertainty of applying meteoric beryllium 10?
That's also mentioned in the talk. So for this equation, each parameter has its own uncertainty. So we need to constrain this uncertainty in a specific case. I mean, for example, in the Taiwan case, we go to sample the terrace profile to constrain this parameter. And we go to Taiwan to collect the rock sample to constrain this parameter. So there is definite uncertainty, but you have multiple approaches to constrain this uncertainty.
Okay, thanks. Maybe I needed to read more. Thanks.
Yeah.
Thanks very much.
Good luck.
Yeah, Joseph in the chat also mentioned the lab work is much easier. So, okay, anybody else? Okay, and if not, Kat, thank you again very much for contributing this wonderful talk. And I think now we understand much better, why, how, quantitatively Taiwan, the small island, able to contribute so much terrestrial sediment to the surrounding ocean. So that's a great work, but still have many unknown, many room, many space we can continue work on. So Professor Shu Ye, you maybe should hire Deng as your assistant, or maybe get other new graduate student to continue this work.
Yeah, thank you, Paul.
It's a great work. It's very good. Maybe you can look at some South Asia or some Himalaya or some other Alps in Europe or South America. I think like Chile, along the South American Andes mountain, for our comparison, that would be great. Future. Okay, if no other question, and we'll also say Happy New Year to our, Asian colleague and student. So otherwise, I will see you next week.
Okay.